Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 23 on nonparametric methods. These are methods that we use typically when the model assumptions of traditional methods do not hold. So we came down here to nonparametric methods, Class 23, and there is a file here, so this is a separate assignment, and I will go ahead and save that markdown file to my classwork folder, open RStudio, and get started. I need that folder. Well, that started very slowly. Sorry for that slow start. All right, 23. First thing to do when you have a file is set the working directory to that source file and knit it. And then we'll read through the assignment. Should take just a moment. Sometimes I get this error when it has trouble writing with this markdown file. Just knit it again, and it usually works the second time. I've only just started getting this error in the last 6 months. Okay, worked just fine that time. We'll open this in the browser and zoom in a little bit. There are 2 parts of this assignment, and each part you'll answer in line with the rest of the assignment. I do source the ADA functions.r file for this assignment. All right, so the first part is some paired comparisons of the sleep remedies. So we've seen this data set before, and we have these 10 people who took a sleep remedy A and sleep remedy B, and we want to know how much more sleep did they get than usual. And their difference between sleep remedy B minus A was a positive number, about an hour and a half. And so people are sort of gaining sleep. When we looked at the bootstrap sampling distribution of the mean, it looks like we've got some deviations from normality. In particular, the red curve is the normal distribution, the black curve is the smoothed curve based on the bootstrap sampling distribution of the mean. And because of this one observation out here in the right tail, whether that value is included or not, basically is causing some right skewness in that black distribution. So we have some, the black line undershoots the normal on the left tail, overshoots in the left middle, undershoots in the right middle, and then sort of overshoots a tiny bit. It's basically the same on the far right tail. So what do we do? Well, we've got a few methods that we can use. These are 2 methods that you learned about in the lecture notes. One is called the sign test, and the other is called the Wilcoxon-Mann-Whitney test, which we'll just call Wilcox or Wilcoxon for short. And these have different model assumptions built into them. The sign test has no distributional assumptions, whereas the Wilcox assumption is that you have symmetry. And so these are, you'll need to go back to lecture notes is what I recommend, and write out the assumptions that you see there. So let's get started with the sign test. First, we're going to state our hypothesis in words and notation, just as we did in the previous assignment with this data. And we need to specify which parameter is being tested. Are we testing the mean? Are we testing the median? Something else? Then we'll write some R code and look at the results. We will need this other package, BSDA, for the sign test. I'll show you how to get that. And just for a change of pace, instead of the standard 0.05 for the type 1 error, the alpha level, we instead will use 0.1 for this assignment. And then we'll state our conclusion. After that, we will that will be our hypothesis test. And then we're also going to construct a confidence interval for the median using the Wilcox test. Okay, so the sign test we're using for a hypothesis test, and then a confidence interval we'll use the Wilcox test. This is just to have practice using different methods for different things. If in practice you would determine whether or not you've got a symmetric distribution for the Wilcox, or you don't want to even make that assumption for the sign test, and use one of those two methods for both a hypothesis test and a confidence interval. Okay, but I'm just trying to give you some exposure to multiple things. All right, in fact, let's take a quick peek over at the lecture notes. So I'm going to scroll up to the, okay, so I've paged up a lot now, to the course notes. Here is the chapter title, and if I scroll down to chapter 6, that's the nonparametric methods, we'll open the PDF file and just do a very quick review here of the sign test for the population median. So that tells us what the parameter is that we're going to need, and the Wilcoxon sign rank test. Excuse me, I did make a mistake when I mentioned earlier Wilcoxon Mann-Whitney. That's only for 2 sample. Wilcoxon managed to get it done himself when he just had 1 sample. So let's scroll down to page 198 is where the sign test begins. Well, that's what it said. There it is. Sign test assumes that you have a random sample from the population, and that's it. No assumption of the population's shape. And it provides a inference about a population median. So instead of the mean mu, we will be using, let me make this a little bit bigger. Instead of the mean mu, we will be using instead ADA, but it sort of looks a little bit like an M. Anyway, we're going to use the Greek letter ADA for the median. Okay, so that's this is what the hypothesis is going to look like for us. Let me jump down now to the Wilcoxon test. There we go. And here we've got an assumption that the population has a symmetric distribution. And of course, if a distribution is symmetric, then it works for either a population median or a mean, because for a symmetric distribution, the mean and the median will be equal. Okay, but I think we will typically think of the Wilcoxon test to be used for a median. Okay, and then there's some details there. So that's just a very quick review. Let's get to work on this assignment. All right, so we've set the working directory. Let's go ahead and run these lines. We've got the tidyverse in there and the ADA functions. We need to load this data. So we'll run that code chunk, and it makes some plots for us. And we can run the bootstrap resampling. Okay, we see the same results in the plotting window in the bottom right as we saw in the HTML. And now I have not given you a lot of structure here. You guys are growing up. You can do more on your own. So our hypothesis in words and notation. So I'm just going to go over to the lecture notes for the sign test and draw my hypothesis from here. We wish to test the null hypothesis that ADA, the median, equals a specific given value. And I'm just paging down for a moment just in case that there's another place where I sort of laid this out in a slightly better way. It looks like I did not. All right, anyway, this is good enough. So we will I'm going to copy this over, but it's not going to really look correct. So I'm going to do this correctly. $H underscore 0 colon slash ADA, that's the Greek letter, slash ADA underscore 0. Okay, and our ADA naught for this difference in sleep remedies is equal to 0. Is the difference equal to 0? Versus the alternative, and our alternative in this case is not equal. You know what? We don't really need this ADA naught in here. Let's just make it 0. Not equal is slash NE. Okay, and we need to define some notation also. Let ADA be the population median for the difference in sleep remedies B minus A. Okay, and then we stated the null hypothesis in notation and then in words. Let's see, so we're testing, let's scroll back over here for a second. Sorry, I'm reading through. Well, I've got the notation there, but I didn't give the example of words. So the alternative hypothesis is the median difference in sleep remedies B minus A different from 0. Okay, the only real difference here from what we've done in previous videos is that instead of the word mean, we've replaced it with median. All right, so now we're going to run some R code. Let's go back over to the lecture notes and find the sign test. So here is library BSDA, and here is the sign test. And you can do it as I did it here in the lecture notes, where you run the library and then run sign test with all caps, or you can do BSDA double colon, and so this syntax means that you're running the sign test function from within the BSDA package. All right, so we just need to create a little vector here. So let's see what our vector is. We've got dat sleep $D for those differences. Very good. Let me do one more thing. I'm going to take away this prefix, even though I prefer it as someone who codes a lot. I think it's sufficient to run the library. So let's just take a quick look at the function for sign test. We've got sign test X and Y. I think it allows you to do a 2-sample test. MD, I think, is the median difference, and the alternative you need to specify could be one-sided or two-sided, probably less or greater, and then a certain confidence level. So confidence level, I believe I asked for an alpha equals 10. So that means we're going to need to specify a different confidence level here of 0.90. All right, let's scroll down through some of the options here in the help and just make sure we understand this correctly. We've got a numeric vector, that's very good, and Y could also be a numeric vector. We don't have a second one. MD is the median specified in the null hypothesis. The alternative is two-sided in our case, but we could do a one-sided test. So the default of two-sided is perfect. Confidence level we've already specified, and I'm scrolling down a little bit and everything looks great. these are the values that come out of the object. So let's put the result here, result of the sign test. And we'll run this, and let's also print it out. Okay, I've talked about the results in the lecture notes a bit about these confidence intervals and the lower and upper achieved confidence intervals, as well as the interpolated one. For because of the way the sign test is computed based on the binomial distribution, we cannot necessarily get exact confidence levels with small samples, or even with large samples, but we're often not even very close with small samples. Anyway, the interpolated sort of provides a way of getting something close to the confidence level that we requested by interpolating these endpoints. And I think it's just fine to use that interpolated confidence interval. Anyway, we are doing a hypothesis test, not a confidence interval, and those values are up here near the top. We had S, I think, is sort of like the degrees of freedom. It is, or it's the test statistic is S. The p-value is 0.02, and the alternative is the true median is not equal to 0. So that's correct. We've tested everything. The median of 1.25 looks about right based on the plot in the bottom right. So it looks like what we've done is correct. Okay, it's always worth doing a bit of a reality check after you see some results. All right, so one object here is $p-value. So we can use that in our interpretation of in our conclusion. Okay, our code and results for the test. That is, so we've done that part. Now the conclusions based on the test. All right, so because the p-value that equals this p-value down here, and we can, we can round that to 3 significant digits. Let's just highlight and run this and see what we get. 0.0215, that's just fine. Because the p-value is less than 0.10, that's alpha, because it's small, right, the p-value is evidence in favor of the null hypothesis. How likely does the null hypothesis seem based on this data? The p-value is small, so we reject the null. We reject the null in favor of the alternative. Oh, I realize I may have just made a mistake up here when I stated my hypotheses. I've got null and null, and the alternative. Okay, so I didn't have a letter A here before. When I did copy and paste, I had H0 2 times. Okay, I've corrected that. And what's up with that additional space? Okay, we're writing a sentence down here. Because the p-value is less than 0.1, we reject H0 in favor of the alternative, concluding that the median. So now we go back to the statement of the hypothesis, basically, concluding that the median difference in sleep remedies is different from 0. Very good. All right, I feel pretty good about this so far. Let's save this and knit it just to make sure that everything's running. I'm quite confident that everything's running, but I guess I'm showing this idea because if At this point, we know all of our code works. So if something breaks in a little while, we know that it's not the code for the problem that we just solved. Here's the results. We've got eta is the population mean, is 8 equal to 0 or not, and is the median sleep difference, difference in sleep remedy is different from 0. Okay, we scroll down, we load the library, we run the sign test, we have our p-value here, and because the p-value of 0.0215 is less than that, we reject in favor of the alternative and conclude that there is a difference. Okay, feel pretty good about that part of the assignment so far. Let's move on to the confidence interval based on the Wilcox test. Okay, so let's do the same thing. In fact, I'm just going to go up and copy the code for the sign test and replace the functions. So result Wilcox. And now we don't have this library. I forget where Wilcox is. Let's go look. I think it's in the stat. Yeah, it's in the stats package, which is loaded automatically. Okay, so we have the Wilcox test, and I believe the syntax is basically the same. You put in the data, x, you can specify the alternative, and we have a two-sided test, so we keep that. We have a confidence level that we need to specify, so that's this here. And notice that there is a very important piece here. Confidence interval equals false. That by default, in fact, let's run this and look at the result. By default, it only computes the hypothesis test and does not compute the confidence interval. The reason why is because the confidence interval is computationally intensive to compute. And so it is only computed upon request. So now if we run this with true, we have some additional output. Okay, let me scroll up just a little bit. This was the output at first, and if I scroll down, now we have this additional output. In particular, that's the part that we want, the 90% confidence interval. It does say that it is using something called a continuity correction. This is typically a good thing. We have a very small sample, and it's giving us a way of getting a confidence interval, just as we did for the sign test. You'll recall that there was an interpolated confidence interval here, and that continuity correction is also an interpolation. It's sort of smoothing a jagged distribution caused by a small sample. Okay, so we have our confidence interval. Let's go find the objects that will give us the confidence limits right here. Okay, so if we do bracket 1, that's the lower bound, bracket 2 is the upper bound. We've got a way of typing these out automatically. I'm going to just copy the text here that we can put into our response. All right, our code and confidence interval for the Wilcox test. Okay, so we've run that, and now we can state the confidence interval. In repeated samples, we a 90% confidence interval for the median will contain the true population median 90% in 90% of samples. We obtained, or I guess our 90% confidence interval for the median is, and then we can put in our bound. So we've got parentheses, and in those parentheses we're going to put two numbers, right? So we're going to do the first one is there, comma, The second one is there. And then we just need to drop our code in there. So here is the code that we copied. I'm going to put the first one here, and let's do it to 3 significant digits. And we'll just copy the same thing and change the index from 1 to 2. And we've got our 95% or 90% confidence interval for the median. Okay. What is the assumptions for the test? Recall from the lecture notes that when we looked at the Wilcoxon test, the Wilcoxon procedure assumes you have a random sample from a population with a symmetric frequency curve or a symmetric distribution. That's it. What the heck? We don't need these stars to make bulleted lists, but it does make reading it a little easier for the grader. Determine the appropriate method for a confidence interval, either the sign or the Wilcoxon, and then present and interpret a 90% confidence interval with reference to the population parameter. Okay, so this is asking me, should we use the sign test or should we use the Wilcoxon test? And so we look at the distribution that we have on the right. We have a sample of size 10. Do we think that the assumptions for the Wilcoxon test are met? If so, then we can use the Wilcoxon test. Otherwise, we must use the sign test. Recall that we can always use the sign test, but if possible, we'd like to use the Wilcoxon test because it is a more powerful test when the assumption is met. So do we think that this is a symmetric distribution? I'll give you my opinion. It looks like, well, we have this one outlier. Okay, so occasionally you might get something strange. So I'm not going to let that one be the only source of influence for my decision. In fact, let me zoom a little bit and make this a little wider. And if it's a little shorter, it might also be a little easier to look at. So I'm interpreting this shape right here for the middle part of the data, right? There's one outlier to the left, there's one outlier to the right. But what is the middle doing? The middle looks like it's a bit right skewed. Now I recognize that we only have 10 observations. I show in the chapter even that, I forget if it's in this chapter or not, that when you draw many times, yeah, I have it in a different chapter. I show somewhere where when you draw multiple times from a normal distribution with small samples, your distributions can look like anything, almost, if you got only 10 observations. If the population is truly normal and you draw 10 observations, you have very little information to say this is normal or not. So this is actually quite consistent with a sample size 10 from a normal distribution. However, we should interpret the data the best we can and make a decision. And I would say that this data looks a bit right skewed. There's right skewness in the middle of the data, and this outlier on the far right also is consistent with a right skewed distribution. So I recommend being a bit conservative here. It's one of the few places in my life where I am conservative, politically and safety-wise when I'm flying airplanes, and things with my son. But I guess the point is that let's be conservative and not assume that we've got a symmetry, but instead go with the confidence interval from the sign test. So I will say, because of apparent right skewness, we will not use the Wilcoxon test, which requires symmetry. Okay, so the way that I've answered this, the way I've stated this, I've given my decision and I've stated the assumption that it violates, right? If I just say, let's use the sign test, that doesn't actually demonstrate knowledge. Okay, so because of right symmetry, we will not use the Wilcoxon, which requires symmetry. Instead, we will use the sign test, which has no distributional assumption. Okay, so once we've decided which one, then we're to present and interpret the 90% confidence interval. So we've got that from up above. We ran the sign test. Here it is. If I highlight this line and press Control Enter, it submits it to the bottom. And let's go find this object in the results for the sign test. Press Enter, and if we get the lower bound as the first one and the upper bound as the second one, we've got the confidence interval right there. So I'm going to steal the text that we wrote before and paste it down here for the result of the sign test. So instead of the result for the Wilcox, we've got the result for the sign test, lower bound and upper bound. And we need to make sure that we state and interpret. We gave an interpretation before, but it's asking for it again here. So I'm just going to copy and paste this down there. In repeated samples, a 90% confidence interval for the median will contain the true population median in 90% of samples. The 90% confidence interval for our sample, 90% confidence interval for the median for our sample, that's a slightly better way of writing that, is that right there. All right. I made a couple very small changes. So, okay. Very good. I think that's everything for the first part of this assignment. Let's save this, knit it, and review the second part of the assignment. All right, there we go. Refresh. And the 9% confidence interval for the median. Okay, and there is our result from the sign test. Okay, looks good. All right, part 2. The number of breaks in yarn during weaving. So this part of the assignment is about analysis of variance. We're going to have multiple groups, but we can't use the standard ANOVA model because the normality assumption isn't met. Okay, so this data set gives a number of warp breaks per loom, where loom corresponds to a fixed length of yarn. So in a loom, right, when in weaving, you've got the warp threads that go up and down, and you've got the weft threads that go white and weft. That's how I remember it. They go, the weft goes right and left, as you in the shuttle that goes back and forth. And we want to know about the breaks in the warp threads that go up and down. We'll analyze wool type B. So there's a data set there's a package called datasets right here. And in that data set, or in that package, there's a data set called warp breaks. And there's 2 types of wool, and we're going to use only wool type B. Okay, back to the description. So in the data set, in the original data set, we've got the number of breaks. we have the type of wool, either A or B, we're using B, and we have a tension factor. So how much stress is on the wool, either low, medium, or high. So we read in the data set from the data set's package, and we look at the warp breaks structure, and it's exactly what we talked about right there. We have breaks, which is numeric, and the other variables are factor. If we filter based on just wool equals B, then we're gonna drop the wool variable because we no longer need it, right? A select statement selects columns, and minus removes a column. So we end up with a data set that is only wool type B. It has the number of breaks, and it has the tension levels. All right, so let's take a look at the plot, and we'll discuss them. You know what, these box plots don't look typical, do they? Because we don't have whiskers. And I've got some comments up here. Okay, notice in the plot below that I include the points, the median, and the IQR, so the middle 50%. Because there are only 9 observations per group, the box in the violin plot that I would typically also include becomes distracting and less informative. I mean, with very small sample sizes, the salience of individual values should increase relative to the summaries. So I've got just the median. Actually, is the median the red diamond? Let's scroll up and take a look for a second. Here's stat summary. The function is median, and that is the point. Shape 18 is the diamond. Okay, so I've plotted the diamonds. The diamonds are medians, and you can see that they're right in the center line of that interquartile range, right? And what do we think? Do we think equal variance? Do we think normality? It's really hard to say with small samples. There is some suggestion here that the high tension maybe has a smaller variance than the medium tension and the low tension. In fact, the higher the tension, the fewer breaks there are. That's sort of interesting. On the right-hand side, I've done the same thing, but I've just plotted it on a log scale to see whether we can improve the situation with equal variance. I think it probably improves a little bit. All right, so let's note some summaries. Oh, this is old, an old way to write this code. That's okay. This I will probably, before you get this, rewrite this code in the newer way. But I've got the median and the mean, and the 5-number summary for the low tension, medium tension, and high tension. And the way this code works, if you're ever interested to use this by function, is you give it the numeric variable, comma, the grouping variable, comma, and then the function you want to run. So for each tension group, I want to get a summary of the number of breaks. That's how that works. Another way you can do that, just to get specific ones, is you can actually define your own function and specify it in this way. I think the tidyverse syntax for all this stuff is a much a cleaner way of doing it. And that's what I already have done down here. So I start with the data warp data set. I group by tension, and then I summarize by these different statistics. And I am dropping NAs in case there are some NAs for the mean, standard deviation, median, interquartile range, and N is the sample size. And the summary is here. So let's take a quick look at the standard deviation. Oh wow, look at that. Okay, so we've got almost 10 and then about 5. So it seems that the high group has about half the standard deviation as the other two groups. So the unequal variance is, in this case, causing us to reject or causing us to not use the standard ANOVA model, because that ANOVA model assumes that the groups have equal variance. And it appears that they do not in this case. Now we also have we have sample size 9 of each group. I think this is quite good evidence we should do something else. So non-parametric methods are available to use even when assumptions for other tests are met, so you can always use them. In this case, we are going to use the Kruskal-Wallis because of unequal variance, however. Use the Kruskal-Wallis rank sum test to assess whether there are differences in medians between these 3 tension groups. If there are, then we want to determine which pairs differ using that 2-sample non-parametric method for the median, the Wilcox-Mann-Whitney test. All right, so I've got some code here to get you started. So I want you first to state the hypothesis, and then I've got code here to do the test. So let's go over to the lecture notes, and Kruskal-Wallis. I did a search for Kruskal. Oops. Try not to page down since it's hard to follow along. Okay, I've got some examples here. I better state some model assumptions state a hypothesis pretty soon that we can follow. But the main thing is that the Wilcoxon, or rather the Kruskal-Wallis, is testing medians instead of means. Okay, so it's clear to me that I need to rewrite some of these lecture notes to sort of follow a better pattern when we're doing these hypothesis tests. Here we go. Let ADA with a certain subscript equal the median, the population median for one of the groups. Okay, so you've got all those medians defined. Then we're going to test the null hypothesis that the medians are all equal versus the alternative that at least one pair differs. That's where we're going. In fact, I'm just going to copy this stuff, even though it doesn't apply perfectly for us. It's a place to get started. So I'm paging down to that first question, state the hypothesis. So in order to state the hypothesis, we need to define the notation. Let ADA equal underscore, let's do, I think we've got low, medium, and high. L, I think we'll just list all 3 of them. Let ADA L, ADA M, and ADA H be the population median for the low, medium, and high tension groups. I hate that we need to write respectively, even though it's obvious, but we do. Okay, so that is the notation. So the null hypothesis, H underscore 0, is these 3 ADAs equal to each other. So I'm just going to copy all this stuff down here and put some equal signs. Okay, are those ADAs all equal versus the alternative? Yeah, so I think I will do not H not. So at least one pair of medians differ. Okay, so we want to know whether all the medians are equal to each other, oh, I need to do words also. Or do at least one pair of medians differ. So that's the alternative hypothesis. Does at least one pair of medians differ in the number of warp breaks for the 3 tension levels? Okay, I think that's pretty good. If you're saying, well, that could be written better, then I agree with you, and you have the opportunity to write it better in your assignment. All right, let's run the Kruskal test here. I did not run the initial data set here. All right, so we'll read the data set in. We don't really need to do the plots or the summaries. We might need the warp summaries. Let's get that in case we do. And the Kruskal test is here. We'll run that. Okay, what do you think? Perform the Kruskal-Wallis test. State the assumptions of the Kruskal-Wallis test and provide support that the assumptions are either met or not. Now, I've given you an example where I'm sort of forcing you to do the Kruskal-Wallis test, but just because I've done that doesn't mean that the assumptions are actually met. Okay, I'm holding you to account to that assumption. So I'm scrolling up to the beginning of the Kruskal-Wallis test here, and the procedure assumes you have independent random samples from populations with frequency curves having identical shapes and spreads. Okay, so I'm going to copy that. I go on to say the Kruskal-Wallis ANOVA is essentially the standard ANOVA based on rank data, and it basically just relaxes the normality assumption. It does not relax the assumption of equal variances, because identical spreads means that the data are spread the same amount. You know what? Let me run the plotting code too. So we have a plot over here. And I don't care about the version on the log scale. Oh, I guess I just called it P. Okay. So this is the data that we're testing. Okay, so I've stated the assumption. The procedure assumes you have independent random samples from populations with frequency curves having identical shapes and spreads. That's the key part. I'm going to just bold that with a double underscore. So, and provide support that the assumptions are either met or not met. Well, the plot suggests that there's less variance, and the table that we had from before, this summary table, suggests that the standard deviations are different. So I'm going to say no. The assumption of spreads being equal is not met because the high tension group has a standard deviation roughly half, that's 4.89, of either of the other two, groups. So I'll do L is 9.86 and medium is 9.43. In terms of shapes, I think maybe the shapes are about the same. I'm not too stressed out about the shapes. I'll say the assumption of equal shapes does not seem to be violated. All right, so in this case, what would we do? We would probably go on to find another test. Alternatively, something that I show you in the notes is that if we find a transformation of the response variable that does lead to these assumptions being met, because the median does not depend on the distribution, you can actually change the scale without changing the ranks. And because the test is based on ranks, any transformation of the response variable is appropriate. Now that sort of leads us to this plot where when we look on the log scale, are the shapes and the spreads equal? Okay, so let's go take a look at that. We created this summary, and why don't we add a few more responses. In particular, we're sort of interested in the standard deviation, so let's create at the end standard deviation for log 10. And we're going to take the log 10 of the breaks, and we'll recompute these summaries. Okay, so this is looking a bit better, right? Before, the standard deviation was half as big for the high group, and now it's 2/3 as big as the other two. So that's sort of telling me that maybe with a sample of only size 9, maybe this is not so different. So I will add to my comments about the model assumptions. However, on the on the log 10 scale, the standard deviation is about 2/3 as large for the high group, high tension, compared to the other two groups, which for a sample of size 9 is not a lot of evidence against equal variances. Okay, so I think on the log scale, it seems we don't have a lot of evidence to say that they're different. So I think we can go forward. Therefore, we can go forward and use the Kruskal-Wallis test. All right, let's interpret the results from above. I don't think we've done that yet. We've got this fit, this p-value here. And let's find the p-value in the object. I put a $sign, and now I can find the p-value and press enter. We will use this in our response. So interpret the test results above, and just for variety, we're using 0.1. Because the p-value, which is equal to that to 3 decimal places, is less than 0.10, right? We have 0.03. We reject the null hypothesis. In favor of the alternative, concluding that. And then we can go up and use the text from that we wrote from before. Okay, that at least one pair of medians differ. That, concluding that at least one pair of medians differ in the number of warp breaks for the 3 tension levels. Period. All right. And then we've got some follow-up pairwise comparisons. Now we used the Kruskal-Wallis test to do the ANOVA. So recall previously when we did ANOVA, we did analysis of variance, and then we followed it up with 2 sample t-tests. The ANOVA test uses a normal assumption. The t-tests use a normal assumption. So we're going to do something similar here, which I discussed in the notes. We use a Kruskal-Wallis for the median for the ANOVA style test of multiple groups. And now we're going to do a follow-up pairwise comparisons using the Wilcox test. It would also be appropriate to use the sign test here. And so, let's see. I think this is just fine. I could have written better code, but this code is just fine. Okay, so I'm using the Wilcox test, where breaks is the response variable, tension is the groups. I'm saying which data set I'm using, and within the Wilcox test you can specify a subset. And actually this is pretty good code. I'm saying for the first test, tension needs to be in the groups either L or M. So I'm comparing the low and the medium tension in this first test. The second test does the same thing, but it's low versus high. Let's put this over here. There we go. Low versus high. And the third one is medium versus high. So in a fairly tight code, if you write the code this way, then you just copy a bunch of lines and you're walking through each pair of groups in this ending statement. It's a fairly tidy way of doing it. All right, so I'm going to run that, and let me scroll up and see the first result here. Here is the Wilcox code that I just ran with low versus medium. We have a p-value of 0.96. So low versus medium, that's these first 2 groups. To me, those medians look about the same. So that we're getting basically a conclusion here that consistent with the null hypothesis that the medians are equal. This looks pretty good. All right, let's scroll down a little bit. We've got low versus high, so that's the first group versus the last group. There looks like there's a big difference, and the p-value is 0.03, and so the hypothesis test agrees with what we see by eye. Similarly, medium versus high tension has a p-value of 0.02. Okay, so what we see by eye is what the tests concluded also. All right, so the last 2 parts, interpret the pairwise comparisons above by saying which pairs differ at a Bonferroni corrected significance level. All right, so Bonferroni takes the significance level that you've got and divides it by the number of comparisons. So if we take a look just at what this number is, all right, you can't do that. Copy, paste, 0.03. So that is the level at which our p-values need to be below in order to reject the null hypothesis. I didn't assign any of these Wilcox tests to any variables, but we could do that to pull out the p-values. Alternatively, we can, in this case, just sort of use our copy and paste down here. So that is low versus medium. Then we've got low high, and we've got MH for medium high. Okay, so I'm just creating some temporary place to copy some things. 0.03, oops, 0.03, and then the last one, 0.1018. Oops, did it again. Okay. And we need each of these, or any of them, to be less than that 0.0333. Okay. So let's see, this one's greater than. This one is greater than. Rats, just a little bit bigger. And that one's smaller. So those are our main conclusions. Now we can do some writing. I guess one way to do it is comparing low to medium. The p-value equals that is greater than that. So we fail to reject H naught. Now we have not yet specified H naught for the pairwise comparisons. Okay, but it's probably worth stating that somewhere. H naught is that the medians are equal for the two groups, two tensions being compared, and HA is that the medians differ. Yeah, that's a good place for a semicolon. All right, so given the text that I wrote, I can basically just, you know what, I'm going to put a few dollar signs around here so that it interprets that greater than sign in a good way. All right, so now I'm just going to sort of copy what I've got here. So this is low to high. And we failed to reject again because that was larger. And then this last one is medium to high. Medium to high. Comparing medium to high, the p-value is that, and it's less than, so we reject H naught in favor of HA, concluding that these two medians differ. These two, we can say population, these two population medians differ. Okay, so this is surprising, right? When you look at the medians, it looks like the median for the low group is sort of higher than the median for the medium group. So why would it reject for the medium versus high versus the low versus high? There's a bigger difference from high to median. Excuse me, there's a bigger difference from the high group to the low group than there is between the high group and the median group. And I think it has to do with at least this point down here for the low group, and possibly a comparison of these two in the rank test. Or it's actually like these values versus the values in the high group. Anyway, the way they all these rank numbers paired up, there's a bit more support for the low group being low when you pair up all the ranks than for the medium group being low, even though the specific median is is actually a little lower for the median group versus the low group. So that's how the calculation works for the Wilcox test. All right. The last part is summarize the results by ordering the means. Now, we don't want to do that. We want to do medians. But you've caught that and made the correction, I hope. And grouping pairs that do not differ. Okay. So in our case, we've got, we want to order the data. So this is a little bit tricky because if we order by median, well, let's see how this can not work for us. Where's that summary? Dat warp summary. So if we go in order by the medians, we've got high is the smallest of 17. Low is the next. Hold on a second. Yeah, I looked at the wrong place for a moment. Median or medium is the next at 28, and then low is the last with a median of 29. Okay, group and then medium. Median. Okay, I'm starting to lose my mind. Okay, that's sort of the key for what's being displayed. Now, what we saw was that low and medium were not different. So let's get rid of these bars and make our own bars. Okay, so no problem with the low and medium group. I'm just going to space over and then connect those. And then low and high differed. Well, how do you connect those with a line? You can't, because medium is in the way, right? You can't sort of like skip over here and just do that. That doesn't really work for a good summary. So I think, unfortunately, the way we need to make this work is we need to swap the order of these. Okay, so now we can, even though the medians are not in order, we have ordered the group in such a way that we can say, okay, the high and the low groups were not statistically different, but the medium and high groups were different, and the high and the medium groups are not connected by a line. So our summary now is consistent with the results. Oops. Okay, and I believe that is the end. So let's save and knit this and do a quick review, and then we are done with this assignment. Okay, so I'll jump down to the number of breaks. We've got the plots that are showing up. They look nice. We've got numerical summaries. We looked at those before. We added the standard deviation log 10, and that is now showing up in our plots here, or in the table. We've stated the hypothesis. Our ADAs for low, medium, and high are there, and low, medium, and high are equal in the null. An alternative is that at least one pair differs, and we've stated it in words as well. We performed the test, and we discussed the assumptions, and we bolded the key assumption here. We discussed the equal shapes, which seems okay. The equal spreads seem to be violated. However, on the log 10 scale, the standard deviation differences are not that big. Therefore, we go forward. We report the Kruskal-Wallis p-value of 0.03. That's less than 0.1, so we reject the null, and then we ask which pair differs. We do our follow-ups. The low versus medium groups gives a large p-value. Low versus high is 0.037. and medium versus high is 0.02. We we define our null hypothesis that the medians are equal for the two tensions being compared. Now this is sort of, right, you'll see that I didn't use notation here. Notation gets a little bit burdensome because you need to, define like median 1 and median 2, where, for the first comparison, median 1 was the low group and median 2 was the high group. In the second comparison, median 1 was the low group, median 2 was the high group, etc. So it's sort of burdensome. So it's a little easier just to say in words that the medians are equal for whichever pair are being compared. All right, we've got our p-values reported. We've got our significance level in there. And we rejected only on the third one, and we failed to reject on the others. And we just discussed this ordering and this grouping. All right, that looks pretty good to me. A+. All right, hope you guys. So I guess the final comment I want to leave you with for nonparametric methods is that they are always valuable. In fact, I think I show an example in the notes where the nonparametric method is actually more powerful than the t-test based on the normal distribution when you sort of have outliers or sort of a lot of variance. There's times when you can really use nonparametric methods to your advantage, and you shouldn't necessarily use them only when your model assumptions aren't met for standard methods. In fact, for a lot of my own work, I will use normal-based methods when they're appropriate, but then we'll also often follow up and do a nonparametric method just as a reality check in cases where models are quite complicated. And there are some cases also where model assumptions are hard to assess, or there's a little bit of question about whether or not the assumptions are met. So in all those cases, I will come back and use nonparametric methods proudly. And we'll just have to explain to my collaborators that no, a t-test is not appropriate here, or ANOVA is not appropriate here, and the appropriate method is Kruskal-Wallis or something else. All right, that's it.